In this video, we're going to talk about some advanced OpenCV topics and how to implement a line following program with ROS. So we're first going to talk about the algorithm that we want to use, and then we're going to talk about how we want to actually achieve it using OpenCV functions. Part of that discussion will be talking about color spaces, such as the HSV color space. We'll also talk a little bit about some more dynamic reconfigure functions that we can use. So in our scenario, we want to be able to follow a line of blue tape on a carpeted floor. So it might look something like this. So in order to demonstrate the algorithm with some simple examples, I have a simplified image that is all black and it just has the white portion as the line. And so in this case, we might say, do we want to turn right, turn left, or go straight? And so in this case, we have the line that's directly in front, so we probably just want to go straight. In this example, we have the line going off to the left here, so we probably want our robot to turn left in order to reorient itself on the line. Similarly, we have this one going off to the right, and if we want the robot to reorient itself with this line, we want it to turn right. And so we have a very simple pattern here where if we have a large white area in front, we want to go straight. If we have it off to the left, we want to go left, and if we have it off to the right, we want to go to the right. Now, of course, there is this example where we don't see any line at all, and maybe we just have the robot stop. Or maybe we have it drive forward and sort of search. That is up to us. So the question is, how do we turn our complicated blue and noisy background image into something that looks like this? And so we've used the threshold function before for black and white images, but here we have some more color, and who knows, we might have certain areas that are white on the carpet or black on the carpet. We don't really know. This carpet could be of any amount of noise on this carpet, and we don't know if we can't just do a simple threshold to threshold out the brighter values of this blue line, because we might have some white papers laying around on the floor or something, and those would mess up our algorithm. So what we really want to do is figure out where the blue line is explicitly. So how do we do that in a way that's similar to our threshold function, but that we can know is going to be correct for our blue line function? So in order to do that, we'll talk a little bit about color space. So up until now, we've been using RGB color space, and a color space is just a way to represent an image using data points. And so here we have the original example that we had in the first video, where we have our image and then we have it separated out into a green, a red, and a blue channel. And so our color space is red, green, blue. And we have a representation of how we can achieve all of the different colors using these three values. So we have a sort of three-dimensional cube here. We have blue, red, and green on these axes, and any combination of blue, red, and green will lead to any other color that we can represent in this cube. And so just with these three simple values, we can end up with a very complex, colorful image like this. But there's other ways to arrive at these colors, not just using RGB. And one of those is hue, saturation, and value. And you might be familiar with this if you've used Photoshop or web design tools or anything really, because most computers use HSV color space for color pickers, because it's very intuitive for humans to sort of understand how to adjust these values. And so the general idea is that we have a hue value, which is this radial one, which sort of defines a base color. And so our base color is either purple or it's red or yellow or blue. And then we have saturation and value, which modify that base color to make it brighter or darker or more vibrant or less vibrant. So saturation is sort of how vibrant the color is. So here at low saturation values, we have very plain, just black and white, and as we increase it, the color gets more and more vibrant. And the value is sort of the brightness of the color. So we start with black at a value 0, and then it increases as it goes up to that base color. So here's a concrete example of what these channels now might look like. And so we have our base image here, and the easiest one to sort of see is the saturation one. So we have this very bright, the bright feathers of the bird, saying that these values of the bird are very, very highly saturated, whereas the background is not saturated, which is why it looks darker in the background. We can sort of see that because the color of the feathers is very bright red, and then the background is sort of this dull greenish color maybe, and that just has this darker saturation value. We can also see in this one here is sort of the value, which is sort of the brightness, And we can see again that the bird has a brighter color and the background is a bit darker, and so we see that the value here are brighter and then off to the sides is darker. Now the hue is a bit different. This one is a little bit harder to sort of grasp with this representation, but what we can see from it is that we see these blue areas of this bird here. This feather here is blue. We have a little bit of blue here, and we see that they all have a similar looking hue value over here. So all of this and this over here, represented by this blue color, have a sort of similar hue value. So let's look a little bit more about how to grasp around this idea of hue. And so to do that, what if we have an image that looks like this and we want to pick out the green leaf? So we want something as a result that looks like this, where we apply our threshold, but instead of doing a threshold for brightness, we want to do a threshold on the color green explicitly. So we want to mask out everything else. And so how might we do that? Well, first we need to convert the image into the HSV color space. And so this is the very first step that we did in some of the previous examples, but instead we converted it to a black and white color space because that was what the threshold function wanted. So here we have the exact same call, CVT color. We have our input image, which is our RGB, and our output image, which is our HSV. That one is defined here. RGB comes from CVBridge. And our parameter, instead of color BGR to gray, we have color BGR to HSV. And so this is going to convert the color space of the RGB image into this HSV image. Next thing that we need to do is figure out what green is. And so we have this wheel over here that defines the values of the hue values. And we can see that green is somewhere between 90 and 150. All the green colors are going to be somewhere in this triangle. There's never going to be any green, over here and maybe a little bit on these edges. So we sort of approximate and say, well, it's probably between 90 and 150 is where all our green values are going to be. Notice, though, that we don't really care what the value or the saturation is. It could be anything along this axis, and this one is only really showing us the saturation value, but it's similar for the value. We know it could be anywhere along there, but all we care about is the actual hue, which is between 90 and 150. So how do we apply our threshold to look at this triangle? It looks just like this. So we have our HSV image from the previous step, and again we're going to create a storage location called our mask that we'll pass in by reference. And we define these two variables, low and high green, and these are those two values that we picked from before. So we have 90 and 150. So we know green is never going to be lower than 90 or higher than 150, so we have these defined that way. One important thing to note is that OpenCV uses a single byte to represent these values, but since if we look here, this is a full circle, it's 360 degrees, you can't represent 360 in a byte. And so what they do is they actually divide these values by 2. So what they're really using is between 0 and 179. So I usually just use this pattern where I have the actual value that I want it to be, in this case 90 or 150, and then I just put a divide by 2 instead of writing 45 or something like that. I just put a divide by 2 there. So now we want to apply our threshold, but in this case, if we're using colors, the threshold function is called inRange. And so we're thresholding across a specific range, not just the black or white. But the function call is somewhat similar, where we have our input image as the first argument, and then the next two arguments are the upper and lower bounds. So it's actually the lower first and then the upper. So here we're defining our lower bound to be that 90 and our upper bound to be 150 for the hue. But notice that the saturation and value numbers here are actually between 0 and 255. So what we're really saying is they could be anything. Because 0 and 255 are the min and max values of the byte, and so we're saying I don't care what the hue, I don't care what the saturation or the value are, I'm just looking at the hue. And after applying this operation, it'll go into the last parameter, which is the one we passed by reference, the mask. And so after this function call, we should end up with something that looks like this. Here's our input image, and here's our mask. Everything that satisfied that requirement of being in the range, so here our green leaf, is left white, and everything else is black. There's another operation that might be very useful, and that is called the dilate function. So normally, when you apply these functions, you end up with, we can see there's a little bit of green over here in this leaf, Maybe here is some greenish color, and then around here we have some sort of red bleeding in, and so you end up with a bunch of noise. And so in order to get rid of that noise, you can use the dilate function, which is sort of like a blur, but it only applies to black and white. And so here we have an example of what that might look like. We have this letter here that has a bunch of little black speckles in it, and the edges are kind of rough, and we want to smooth that all out. And so if we apply the dilate function, we'll end up with something that looks like this, where we sort of smooth out all of the noise, and we get a really nice smooth color space right here. So how do we do this? It looks just like this. We have a similar pattern. This is very common with OpenCV, right? We have our input value, which we got from the previous step, and then we have a storage value. And then we have this parameter, which is our dilation size. And this is approximately how big the biggest speckles of noise you expect to have. So in this case, they're like, I don't know, 3 or 4 pixels or something, so I chose 5. Generally, you don't want this to be too high. If it's way too high, this will just like inflate. It'll look kind of silly. You're welcome to try it, but generally you want this to be somewhat small, so I picked a value of 5. Now this whole chunk of code down here is to create this thing called a structuring element, and this structuring element is sort of like a parameter that's used in all sorts of functions, including dilate. For dilate, it's actually a sort of simplified version of this, where you can use this formula that you see over here to create your structuring element from your dilation size. So this code, you pretty much just want to use verbatim given your dilation size. It just creates a formula that creates a structuring element that fits with this dilation size. The actual function is down here, and it follows, again, a similar pattern. You have your input, you have your output, and then you have some parameter that defines how you want to call this function. So we have mass dilated, and element. And after you call that function, you'll end up with something that looks like this, where you have the undilated version and the dilated version. So this is just an example of what you might end up with. This is one I found on this blog right here. So you can look here, and you can see some more examples of this guy playing around with OpenCV and some of the functions. You can learn about it there. But he has this example where he has certain values, and all these different values have different thresholds or different HSV values, and you can see they're all sorts of noise, and they don't look super great. And how do you determine what the best values should be for your program? And so the best way to do that generally is by experimenting with them, moving them around and seeing what they look like. Of course, we don't want to change our values in our program and recompile it every time, because that's very inefficient, and the world around you changes so much that you want to be able to adjust them very quickly. And so of course we have our tool dynamic reconfigure to do that for us. So here I have an example of the same program that's looking at this scene of a couple of objects, and I've adjusted the parameters so that in one instance they're looking for these red objects, and in another instance it's looking for the blue ones. And the parameters that I have defined are over here, and they look like this, where we have a low hue and a high hue, just like the values we had in the steps previous. But I also have a saturation and value. In this case, it's just LUM for luminosity, but it's the value. And so instead of doing this step here, where we're just doing a 90 and 150, I'm actually using those parameters for every single one of these values here. So we have a low and high, and then we have a low, high, saturation, etc. That come from each of these. And so now we have a fully tunable in-range function that we can use to tune it for whatever color or brightness we want. One additional thing to know about dynamic reconfigure, which is handy for this type of tuning, is that you can actually save and load your parameters straight from the GUI. So there's buttons in the top corner. This one here is save, and this one is load. And when you save your parameters, make sure that it'll save it as a YAML file, and make sure you type in .yaml at the end of your file name, or else it won't automatically put that there, and you won't be able to find your parameters if you try to load them again. So make sure you type .yaml. So you type that in and save it, and then later when you relaunch your program and all your parameters are gone because it resets every time, you can click this button to load them up again, and you'll be right where you left off. So that's a few examples of some additional things you can do dynamic reconfigure to support the program. So now you have the tools that you need in order to create the original algorithm that we saw in the previous, in the first few slides of this presentation. You're now able to take a color and segment it away from an image, so you have a black and white, and then from there you can implement some very simple logic to say if the white portion is on the left, the right, or the center, make the robot turn left, right, or just go straight.